Okay, so this problem is from the 2007 Form B exam. It's the first question on the free response, and it's a chemical equilibrium question. No surprises there. The first question on the FRQ is always an equilibrium, so be prepared. So we've got a solid sample of solid U3O8 is placed in a rigid 1.500 liter flask. Chlorine gas is added to the flask. The flask is heated to 862 degrees Celsius. The equation for the reaction that takes place and the equilibrium constant expression for the reaction are given below. So there's the balanced equilibrium reaction. And kind of surprisingly, they give you the actual expression for the case of P. Again, notice the case of P only contains the gases. It does not contain the solids. So solids do not appear in the equilibrium expression. Kind of surprised that they gave you that equation. Normally they would probably ask you to write that equation. Notice that it's the pressure of the UO2Cl2 cubed times the pressure of the O2 to the first power times the pressure divided by the pressure of the Cl2 to the third power. So those coefficients in the equilibrium expression come from the balanced equilibrium reaction. All right, they tell us the system's at equilibrium. They give us the pressure of the Cl2. They give us the pressure of the UO2Cl2. The only one they don't give us the pressure of is the PO2. Notice the relationship 3 moles of UO2Cl2 are produced for every 2 moles of O2. So therefore, the pressure of the CO2 is going to be 1/3 the pressure of the UO2Cl2. Okay? So again, 1 mole of O2 for every 3 moles of the UO2Cl2. So that relationship will tell us that the pressure of the oxygen will always be 1/3. So the pressure of the oxygen is going to be the pressure of the UO2Cl2 divided by 3. All right, calculator out. Go ahead and plug that into the calculator. 4 sig figs, 2.9. Whoops, sorry. 3.245 times 10 to the minus 4th atmospheres. A tiny pressure. All right. Not surprising here. Both pressures of the UO2 and Cl2 and the O2 are very low. The pressure of the Cl2 is high. This reaction definitely has an equilibrium that favors the left-hand side. And therefore, we're not going to be surprised in the next step that when we calculate the equilibrium constant is going to be small. Kind of nice to note. Case of P is less, much less than 1. Okay? Reaction favors equilibrium, favors the left. So, there we go. To actually calculate the case of P, pretty straightforward. We've got the case of P expression. We're just going to now play plug and chug. So now we're going to take all those pressures and plug them in. Let's see. We've got the pressure of the UO. So again, the pressure of the UO2Cl2 cubed, pressure of the O2 to the first power, pressure of the Cl2. Excuse me a second here. Cl2 cubed. Go ahead and plug in. 9.734 times 10 to the minus 4th. That's cubed. 3.245 times 10 to the minus 4th to the first power. And then finally 1.007 cubed. Remember, equilibrium constants do not have units, so we plug those values into our calculators, and we confirm that indeed the equilibrium constant for this reaction is incredibly small, 2.931 times 10 to the minus 13th. Again, anything 10 to the minus 13th, very, very small. So that equilibrium, that very, very small equilibrium constant matches with our prediction and our observation that the reaction lies far to the left-hand side. All right, little thermodynamics here, delta G0. okay, for the reaction at 862 degrees C. I've put a little snip from the AP Chem cheat sheet, and so although you might remember these questions or these reactions, these equations, here it is. If we take a peek here, here's a equation that shows us the relationship between delta G, the free energy, or sometimes called the Gibbs free energy, and the equilibrium constant. There's a logarithmic relationship here. Okay. Couple of things to notice. Again, this reaction, this equation makes some sense. It's always nice to look at a mathematical equation and know it makes a little bit of chemical sense. Reviewing a little bit about delta G is free energy. If delta G is negative, the reaction is spontaneous. Again, this is talking about the reaction going from left to right. So if the reaction is spontaneous going left to right, delta G is negative. And that's another way of saying the reaction has a large equilibrium constant. Its state tends to favor the right-hand side. So if K is big, all right, K is greater than 1, that means delta G is going to be negative. Notice in the reaction, if K is positive, log of K is going to be positive, T is always going to be positive, R is always going to be positive, delta G will be negative. So if K is, I shouldn't say positive here, if K is greater than 1, then delta G is definitely negative. If K is less than 1, okay, log of K is going to be negative. Negative times negative is going to give me a positive. Delta G is going to be positive. So the relationship between delta G 0 and equilibrium constant should make some sense. In any event, we can go ahead and do the equation real quickly. Delta G 0 is going to be equal to negative R. R has a value of 8.31 joules per mole per K. Okay, so that's again the ideal gas constant, but the ideal gas constant in terms of energy units. T, 862, don't forget we've got to add 273, so that's going to be 862 plus 273K. And then finally, we'll just take the log of the equilibrium constant we calculated up above, 2.931 times 10 to the minus 13. So we plug that into our calculator. Notice K is much, much less than 1. Log of K is going to be negative. Delta G is definitely going to be positive. And when we do the calculation, delta G 0 has a value of 315.0 kilojoules per mole. Notice I did it in kilojoules. The problem didn't specify that it had to be in kilojoules, so joules per mole would have been just as good. Okay, good. So there's the delta G. So small k, positive delta G. This reaction would be classified as being non-spontaneous, going from left to right. Entropy change. Again, entropy is a measure of disorder. If we go up and look at the reaction, so I'm going to scroll up here. If we go back and look at the reaction, what's your prediction about entropy? We've got a solid plus a gas forming gases, and therefore we've got more gas particles on the right-hand side, fewer gas particles on the left-hand side. We've got that solid on the left-hand side. Okay, we've got greater disorder here on the right. We've got less disorder on the left. Therefore, the delta S for this reaction is definitely positive. Delta S equals positive. Okay, notice that on the AP Chem exam, they're always going to ask you to justify your answer. Your justification is that the products contain more gas particles than the reactants. Disorder is increasing. Okay? Keep those answers short, informative, and concise, and readable by the grader. Remember, you always want to put a smile on the grader's face. All right, so now we know that delta S is positive. We know that delta G is equal to positive. Delta S is equal to positive. We look at our old friend, and again, these little zeros mean the standard free energies, or just standard entropy. They now want us to know what's the enthalpy change. If we look at a lovely little relationship, delta G0 is equal to delta H0 minus T delta S. Again, if you didn't remember that, it's on the cheat sheet, but I suspect you should know that one. If we rearrange that equation, delta H0 is going to be equal to delta G0. Whoops, hang on. Delta G0 plus T delta S0. Do a little bit of analysis. We've already figured out that delta G is positive, delta S is positive, T is always positive, so this term is positive. Therefore, delta H is definitely positive. And you've already shown your justification by using this lovely little expression. All right. Finally, last part, Le Chatelier's principle. We've got the reaction at equilibrium. I'm just going to go ahead and write that reaction again. So we've got the solid uranium oxide reacting with chlorine gas in equilibrium with UO2Cl2 gas, 3 of those plus oxygen gas. Okay? We add systems at equilibrium. We knock the system out of equilibrium by adding a mole of O2. So we imagine we have some kind of a device on the container that allows us to add a mole of O2. Should be pretty obvious what's going to happen to the equilibrium. Stress is on this side of the reaction. The reaction is going to shift to the left to try to minimize that excess oxygen. In the process, what's going to happen to the U3O8 amount of U3O8? We're going to produce more solid, so the amount of solid, actually just to be official, the mass of solid increases. Okay, again, if that makes sense to everybody, Le Chatelier's principle will produce more of that because the reaction shifts to the right to remove this stress. Or not to remove it, but to minimize it. Okay? Suppose they had asked you how would the oxygen concentration have changed? The new concentration of oxygen at equilibrium would have been greater than the previous oxygen concentration. Okay? The UO2Cl2 concentration would have been less than the original equilibrium concentration. The concentration of Cl2 would have also been greater. So things on this side would have decreased. Things on this side would have increased. Make sense? All right. Good.